Hey everyone, Ricardo here, and in this video I'm going to be showing you how to set up a transformer differential scheme using the SEL 487E relay as an example. So we're going to see how a transformer differential scheme works from a theoretical point of view, and then we're going to see how to program an SEL 487E relay. So stick around till the end to see how to program this relay. Alright, so for a differential scheme and a current differential scheme more specifically, what we're doing is we're comparing the current that enters a differential zone and the current that leaves the differential zone, and then we're comparing the two to see if there's a fault inside that differential zone. And here again, when I say the differential zone, what I mean is the part of the power system that is protected by our differential relay. So let's take a look at an example substation to see how we can implement this differential protection. Alright, so what I have over here is an example substation that we're going to be using as an example to illustrate how we can perform a transformer differential protection scheme. And for this example, we have a 230 kV to 13.8 kV substation. So here you have, let's say, two transmission lines that feed into the substation. So this would be a transmission line, and this over here would also be a transmission line. And they each feed one transformer in this substation, and then those transformers step the voltage down from 230 kV to 13.8 kV, and they feed into a common bus down here. So this is a 13.8 kV bus. So this would be like a typical distribution substation in a power system. Now in this case, we're going to be implementing a transformer differential scheme for this transformer over here on the left. So let me actually zoom in to the transformer, and we're essentially going to be performing a transformer differential scheme that covers this part of the system. So essentially our differential zone is going to go from this CT on the top, so this one over here, to this one over here on the low side. So again, when I say a differential zone, what I mean is the part of the power system that is encompassed by the current transformers, the CTs, that feed into our differential protection relay, in this case an SEL 487E relay. So our goal here is to detect any fault within this zone that I've highlighted here in yellow, and there are a few key points that we need to consider when setting our differential element. First, we need to consider that the current on the high side of the transformer is not going to be the same as the current on the low side of the transformer, even under normal conditions, because we have the transformation across the transformer. Second, we also need to compensate for the CT ratios on the high side and the low side of the transformer, as well as the CT connections. So these can be connected in a Y configuration or a delta configuration. So we need to compensate for both the CT ratio and the CT connection. Alright, so having said this, we first need to come up with a way that we can have an equivalent current on the high side of a transformer and the low side of a transformer. In other words, it is helpful to convert quantities to a per unit system rather than using actual quantities, so that 1 per unit on the high side is equal to 1 per unit on the low side under non-faulted conditions. And this per unit conversion needs to account again for the transformer winding voltages, in this case 230 kV on the high side and 13.8 kV on the low side of the transformer. We also need to compensate for the CT ratios and the CT connections like I mentioned before. Now we'll also talk about how we can compensate for the phase shift across the transformer here in a second, which is done separately from the current magnitude compensation. So there's two things I want to consider, both the current magnitude compensation and the phase shift compensation that happens due to the connections on the transformer. In this case, the high side of the transformer is connected in what we call a delta connection, and the low side of the transformer is connected in what we call a Y configuration. So there's going to be a phase shift that is introduced by that different connection on the high side and the low side of the transformer. But again, that's done separately from the current magnitude compensation. So we're going to talk about that later. All right, so first let's talk about how we can do this current compensation in the SEL 487E relay. And each relay has its own unique way of doing this compensation. So you always have to check the instruction manual for the relay that you're using. In this case, we're going to be using an SEL 487E relay. All right, so the current compensation in this instruction manual specifically is on page 192. So let's go to that part of the instruction manual. So we have the current compensation equation here, and this is what's called the tap setting in the SEL 487E relay, and most relays also call it the tap. So this is basically an equation that is going to allow us to have an equivalent per unit system on the high side and the low side of the transformer. So the goal here is to develop some quantity by which we can scale the current readings on both the high side and the low side of the transformer That's going to equal 1 per unit for our differential element. Now in here you can see that we're considering the MVA of the transformer, so the rating of the transformer, the power rating that is, the voltage on the winding that we're trying to compensate, the CT ratio, and also the CT connection, which is done with this variable over here, C. So again, this is a way that we can say, okay, for a full rating of the transformer, what's the current and secondary amps that the relay is going to see for each winding. So let's go ahead and do this calculation for both the high side winding and the low side winding in our example. And again, remember here that for our example transformer differential scheme, we have a 230 kV system on the high side of the transformer and a 13.8 kV system on the low side of the transformer. Some more information that we're going to need is the CT ratio on both sides of the transformer. In the case of the high side, we have the CT ratio over here. It is a 400 to 5 CT, which equals 80 to 1. And then we have a 5000 to 5 CT here on the low side, which is of course 1000 to 1. So now we can use that equation from the instruction manual and calculate the tap setting for each side of the transformer. Now again, the equation which is mentioned in the instruction manual is this one over here. So we have the tap is equal to the MVA of the transformer times 1000 divided by square root of 3 times what they call V term, which is the winding voltage in kV for that winding, the CT ratio CTR, and the transformer connection C, and this constant C is going to be 1 for a Y connected CT and square root of 3 for a delta connected CT. Now most modern microprocessor relay schemes use a Y connection for the CTs, which is also going to be the case in this example. So this constant is going to be a 1. So now we can calculate this for the high side winding. So we're going to have that the tap on the high side, so let me call this tap H, is going to be MVA, which in our case is 100. So we have a 100 MVA transformer times 1000 divided by the square root of 3 times the voltage of that winding in kV. In this case, it is 230 kV, and this, by the way, is the face-to-face voltage, times the CT ratio for that winding, which in this case is 400 to 5 for the high side winding, which again is 80 to 1. So our CT ratio is simply 80, and again times 1 over here for the constant for the connection type of the CT. So if we calculate this, we get that this is equal to 3.14 amps, and this of course is going to be amps secondary. Now we can do the same thing for the low side tap. So tap L, and here I'm going to use L for low side, is going to be equal to 100 times 1000. So of course the same MVA rating over the square root of 3 times the voltage. In this case, it is 13.8 kV times the CT ratio, which in the case of the low side is 5000 to 5, so 1000 to 1. And again, times the constant for the CT connection, which in this case is a Y connected CT. So that constant is going to be a 1. And if we calculate this, we get that this is equal to 4.18 amps secondary. Now here we can see that the tap setting is essentially a way of saying what's the current that the relay is going to read for that winding if the current that's flowing through the transformer is equal to the full rating of the transformer. So in this case, we have a 100 MVA transformer, and essentially all we're doing is converting 100 MVA to current for that winding at that voltage, and then converting that to secondary current for that winding, which is what the relay is going to see. So that's essentially all the tap is. It's essentially the full rating current for that transformer as seen by each winding on the relay. Now I also created a spreadsheet that you can download. Check out the link in the description below, which calculates the tap settings if you give it the power rating of the transformer, the kV of each winding on the transformer, the CT ratio, and the CT connection. So let me show you that real quick. All right, so this is the spreadsheet. And again, here what I did is I have this spreadsheet auto-calculate the tap settings for both the high side and the low side windings, given some information. Of course, here for calculating the tap settings, you gotta give it the MVA of the transformer, the kV for each side of the transformer, and information about the CTs, both the CT ratio and the CT connection type. And with this spreadsheet gives you the tap settings for each winding. In this case, we can see that the 3.13 matches what we calculated. For the high side winding, we got 3.14 because we rounded to 2 decimal places, so that's the same as this number. And then also for the low side, we have 4.18, which is this number over here. So again, you can download this spreadsheet. I'm going to leave a link in the description below. And I also included here the tripping characteristic for the differential element, given the 087P and the SLP1 and 2 settings. These 3 settings are settings that define how the tripping characteristic of the differential element looks like. And these settings are the minimum operating current, which is the 087P setting, and the slopes for both internal and external faults. And again, those define how this characteristic looks like. This one over here on the right, which is the tripping characteristic for the differential element as it is implemented on the SEL 487E relay. So you can also use this spreadsheet to plot the tripping characteristic for the differential element. Now in here, essentially, we have a plot of the operating current and restraining current. And so basically any plot over here would be a tripping decision by the relay or a no trip decision over here by the relay. And the trip characteristic looks like this. So it's the intersection between these curves. This line over here would represent when the relay is using the slope number 1. And this one over here would be when the relay is using slope number 2. Now the relay switches between slope 1 and slope 2 when it thinks that there's an internal fault or an external fault. If it thinks that there's an external fault, it's going to switch to slope number 2, which is a little bit steeper, which causes the tripping to be a little bit harder to achieve. But it switches to a more conservative setting because it thinks that there's an external fault. So again, you can use this spreadsheet to see what the tripping characteristic is for the SEL 487E relay. And I'm also going to leave a link for our transformer protection course. Check out the link in the description below where we talk about this characteristic in much more detail, as well as other types of protection for transformers such as overcurrent protection and volts per hertz protection, for example. All right, so with this tap setting, essentially we can compensate for the current difference between the high side and the low side windings, but we also need to compensate for the phase shift that is caused by the transformer connections. And again, in this case, we have a high side that is connected in a delta configuration and the low side is connected in a Y configuration. So while the tap settings compensate for the current magnitude difference, it does not compensate for the phase shift that is introduced by the transformer connections. So we also have to compensate for that. Now for this example, and let me actually go back to the one line, the high side currents are going to lead the low side currents by 30 degrees. So there's going to be a 30-degree shift between the high side currents and the low side currents. And again, this is caused in this case by the delta connection on the high side of the transformer. So to compensate this, we can do one of two things. We can either tell the relay that it needs to subtract 30 degrees from the high side current's angle, or we can tell it to add 30 degrees to the low side current's angle. In either case, what we're doing is shifting one of the currents with respect to the other to counteract the effect of the phase shift across the transformer. Now, to accommodate for any possible power transformer connection difference, the relay allows us to shift either winding in increments of 30 degrees. So let me actually go to the section of the instruction manual that talks about this. And that, in this case, is shown on page 191. And we essentially have this table over here. This is basically a complete list of the matrices for shifting currents in the relay. And what this is a setting in the relay by which we can tell it to shift the currents it reads in any 30-degree increment. So for our example, since the low side is lagging the high side by 30 degrees, we need to shift the low side currents by 30 degrees counterclockwise. And we can do this using a setting of 1, which is over here. So this one over here. Now notice here that in this table that we are compensating a 30-degree clockwise angle, and that's shown over here. So for an ABC rotation system, which in this case we're assuming that we have an ABC rotation system, we're compensating a 30-degree clockwise angle, meaning that the low side is 30 degrees ahead clockwise of the high side. Now this is a little bit confusing, and I think the instruction manual actually talks about it a little bit better, or words it a little bit better on page 189. And it's essentially this paragraph over here, which says setting TMCTC, which is the current angle compensation, specifies which compensation matrix the differential element is to use. And pay attention to this part over here. The traditional settings values are 0 through 12. These values physically represent the number of increments of 30 degrees that a balanced set of currents with ABC rotation will be rotated in a counterclockwise direction. So what does this exactly mean? Well, It means that, again, for our example, we would have something like this. The high side currents, let's say high side A phase, would be 30 degrees ahead of the low side A phase current. So the high side is leading the low side by 30 degrees. So if we use a matrix of 1 for the low side, we're going to rotate it such that it now becomes, and let me switch colors, it now becomes in phase with the high side. So that way we're compensating for the phase shift across the transformer. All right, so now we've compensated for both the current magnitude and the phase shift across the transformer. Now let's see how we can program an SEL 487E relay. All right, so what I have over here is an example SEL 487E relay settings file. And here I'm using just default settings for an SEL 487E relay. So let's see how we can program this relay to perform a transformer differential protection for our example transformer. Now there are many settings within the relay. In this video, we're going to be focusing on the transformer differential element. Now for the transformer differential element to work, we need to first define a few things such as the CT ratio, the CT connections, the voltages of each winding, the rating of the transformer, and so on and so forth. So I'm going to show you how to program those into the relay. Then we're going to see how to program the transformer differential settings. And then we're going to program those settings into a trip output. And we're also going to program, of course, the transformer differential element into a trip logic first, which is what we're then going to route to the outputs. All right, so again, these are all default settings. And there are a few settings here that I need to define first. Let's first go to global over here, and let's go to general global settings. These are just general information. I'm just going to fill that out just as an example. So we're going to call this an example station, and then this is going to be a substation transformer. And the nominal system frequency for this example is going to be 60 hertz, just a typical frequency for the power system in the US. The phase rotation, again, is going to be ABC for our example. Now, this is very, very important because the way that we compensate for the phase shift across the transformer depends on what the phase rotation is. So the settings that we're going to do apply to an ABC rotation system. Just keep that in mind. All right, so I also want to go over here to group 1, set 1, relay configuration. And in here, we can give the relay just general information about how a relay is wired. In this case, we have this setting, which is the enable for the current terminals. In this case, we're going to use an S and a T connection on the relay. Essentially, the relay has different connections that you can use. It's got S, T, U, W, and X. So each one of those is a set of 3-phase current inputs that you can wire into the relay. In this case, we're going to be using S for the high side and T for the low side. So in our enable for the current terminals, we're just going to use S and T. And just for the sake of it, I'm going to tell it that the voltage inputs are wired on the V terminals. That's not relevant to the differential protection, but I'm just going to program it just for the sake of it. Now, this is another important setting. So include the following terminals into the differential element. In this case, again, we have a current transformer on the high side that's going to be wired into our S input. And then we have the low side currents that's going to be wired into the T input. All right, so I'm going to leave everything else default. I'm going to focus over here on the current transformer data. This is where we give the relay information about the CT ratios and the CT connections. Again, for our example, the high side is going to be a 400 to 5 CT, so 80 to 1 connected in a Y configuration. Our low side CT is going to be 1000 to 1 or 5000 to 5, also connected in a Y configuration. So that's the basic information that we need to tell the relay, just so that it has some information to program into the differential element. Now let's see how we can program the differential protection. So it's going to be down over here in the differential element configuration and data settings. We have a bunch of settings over here. I'm going to start first with the MVA setting, which I believe is further down over here. And again, this is the transformer maximum MVA rating. For our example, we're just using 100 MVA. Typically, a transformer would have multiple ratings. Just make sure that you use the maximum of all the ratings, typically the force A rating. Now for our example, this is 100 MVA. And I get an error over here, but that's because we haven't finished entering the settings. That's going to go away once we enter actual information. So that's the MVA. Now let me scroll up over here. And again, we're going to use the S and the T terminals. I want the S terminal to always be enabled, so that's going to be a logical one. And the compensation for that terminal, which again is the delta in this case, the high side, I'm going to use that as the reference. So I'm going to use a compensation matrix of 0, which essentially means don't do anything. That's going to be your reference. Now this is important. The voltage on that winding, which in this case is 230 kV. And then for the T winding, which again is the low side in our case, I also want that always enabled. We're going to use a compensation of 1, as we talked about, for the low side currents. So that's going to shift the low side currents 30 degrees counterclockwise, such that it becomes in phase with the high side currents. That's how we do the phase shift compensation. And then lastly, we have the voltage for that terminal, which in this case is 13.8 kV. Now notice over here that the tap S and the tap T settings got auto-calculated by the relay. And these numbers match what we calculated before. So the relay already knows what information that you gave it, which was the MVA, the current transformer data, so the ratio and the connection type, and then the voltages for each winding. It knows how to calculate that internally. So that's what we calculated before. 3.14 for the high side, 4.18 for the low side. Now I'm going to leave all the other settings default down here for the trip characteristic, the minimum operating current, and the slopes. Again, we have a full online course where we talk about all of this in much more detail. Check out the link in the description below. But this essentially tells the relay how to configure the tripping characteristic of the differential element. So a couple more things that I want to do over here is now we've configured our differential element, but we need to tell the relay to use the output of that logic in the trip equation, which is this relay word bit over here, 87R. So I'm going to get rid of this REF trip. And this essentially tells the relay, use this relay word bit, which is an internal tag that the relay uses that's going to become a logical one if it decides to trip on its differential protection element. And I'm going to use that in the trip equation. And now I can use that in my outputs. So for this example, I'm going to assume that we're going to have 3 outputs. Outputs 101, 102, and 103. And I'm going to program all of those to trip XFMR, which is the output, and actually that's just TRP XFMR. And again, this is the output of the tripping element within the relay. All right, so that's how you program the differential element in the SEL 487E relay. Again, we talk about this in much more detail in our Transformer Protection online course. Check out the link in the description below. But here we saw how we can compensate for the current magnitude and the phase shift across the transformer for a transformer differential scheme. Alright, so if you like this video, make sure to hit the like button, subscribe to the channel if you want to learn more about power system protection and power engineering, and we'll see you in the next one.